Valence bond theory. In the valence bond theory, metal atom, under the influence of ligands, can use either its n-1d, ns and p orbitals or ns, np and d, where principal quantum number is same, for hybridization. And after the hybridization, we will have equivalent set of orbitals which are arranged in definite geometry. So this way, valence bond theory tries to explain the directional characteristics of coordination complexes. And further, valence bond theory predicts the geometry of a complex from the knowledge of its magnetic behavior. First, in which out of these two possibilities, which is true, will be predicted using the magnetic behavior or magnetic data of a particular complex. Let's take an example of octahedral complex. Hexa means cobaltate, which is diamagnetic. So diamagnetic means this complex will not have unpaired electrons in cobalt atom. This is a cobalt 3 ion, and d orbital will have 6 electrons, 4 unpaired electrons. 4s and 4p orbital will be empty. Now, during hybridization, what happens? 2 of electrons will pair back to justify its diamagnetic behavior, because if this complex has diamagnetic behavior, which means it should not have unpaired electron. The only way to get rid of unpaired electron is pairing up. So these unpaired electrons will pair up during complex formation, leaving behind 2 empty 3d orbitals. So these empty 3d orbitals will overlap or hybridize with 4s and 4p orbitals. In total, we are having 6 orbitals, giving us a 6 equivalent d2sp3 hybrid orbitals, which are arranged in octahedral geometry. And these empty orbitals will overlap or accept electrons from the strong ligand ammonia, thus giving us a octahedral complex which is diamagnetic in its magnetic properties. Such a diamagnetic complex is or in which we are using n-1d orbitals known as lower spin complexes or lower spin compounds. Another complex is our hexafluoro-cobalt complex, which is paramagnetic in nature, which means cobalt atom should have unpaired electron in this complex. Again, taking the ground state. In the hybridized state, what happens? Our unpaired electron will remain the same. What happens? In this complex, we are having empty 4d orbitals. 4 and 2 empty 4d orbitals will be used for hybridization, giving us sp3d2 complex, and unpaired electron will remain unpaired in case of cobalt complex of fluoride. That's what we get. Such complexes are known as the high spin complex because they are having a better spin and more number of unpaired electrons. Next theory to explain the behavior of coordination compound is crystal field theory. Crystal field theory treats metal ligand bond ionic and their interaction with each other purely electrostatic in nature, mean they consider the ligands and metal as point charges. Again, we having here isolated atom which having a d subshell in its outer electron configuration, transition element, and all d orbitals are degenerated, means all 5 orbitals having the same energy level in an isolated state, because the all orbitals are equivalently positioned, so more or less their energy levels will be same. So orbitals that have the same energy level are known as degenerated orbitals. So we have 5 degenerated orbitals. Now for the complex formation, when an active field due to ligand, like we having aniline, ammonia, water, they interact with the d orbitals electrons of metal to form a complex. Such a repulsion is more for the metals d orbitals directed toward the ligand than the d orbitals which are away from the ligand. In simple way, the d orbitals which are directly pointed toward the approaching ligand face greater repulsive force compared to the orbitals that are arranged in space away from approaching ligands. This is a 3D arrangement. We having a 6, let's say, ammonia molecules approaching the metal. During their approach, the molecule that approach directly along the axis, the d orbital along the axis will face greater repulsive force, and the orbitals that are arranged in between the axes, they face other sort of repulsive force. In such a case, d orbitals will not retain their degeneracy, mean the energy levels of all d orbitals will not be same, and depending upon the kind their energy levels or repulsion from the ligands, they will split. Let's see how these d orbitals will split. We see in case of the octahedral geometry we are talking about, we having a dz square and dx square. These orbitals having d or dz square and dx square minus y square, these orbitals are directed directly toward the axis. So because these all our ligands approaching along the axis, either negative axis, positive axis, so that's why these orbital faces greater degree of repulsive force and their energy will go up. So they make one level known as the Eg. Another level, the orbital lying in between the axes, they experience lesser repulsive force compared to our directly axis directed orbitals. So T2G level experience lesser repulsive force known as dxy, dyz, dxz. These 3 orbitals make a one set known as T2G. They make a lower energy set in case of octahedral geometry. We are splitting the orbitals on the basis of energy. So crystal field splitting is dependent on the orientation of ligands around the metal atom. Depending upon the approach of the ligands, our degenerated orbitals will split into 2 levels. This is octahedral complex. And in case of a tetrahedral complex, the crystal field splitting will be different than octahedral complex. As we treat these interactions purely as electrostatic. Here we saw a splitting, dx squared, dz squared and dxy. This is upper energy level because of these higher interactions along the axes from ligands. When our ligands approach, first all 5 orbital energy will go up. Then further approach will split them in 2 parts. One is a higher energy or the axis directed orbitals known as EZ level, and bottom T2G known as dxy, dz, dyz and dxz orbitals. And there are 3 orbitals here. Here it is 2 orbitals in upper energy level. The first level to which they are raised because of these electrostatic interactions known as barycenter. The crystal field splitting depends upon the charge on the metal ion and field produced by the ligands. In spectrochemical series, ligands are in the order of their increasing field strength. So first you remember, this barycenter energy will happen in such a way that 2/5 difference from the barycenter is 2/5 times lower than octahedral field, and these higher energy orbitals are 3/5 octahedral energy higher than the barycenter. Now let's have a brief look at spectrochemical series. This is a spectrochemical series, and it is the ligands are arranged in their increasing field strength. So what we see here, iodide is the weakest field ligand, bromide, thiocyanide, chloride, sulfide, fluoride, hydroxide, oxalate is better ligand than these one, water still better than oxalate. Then we have isothiocyanide, EDTA, amine, ethylene diamine, cyanide, carbonide. So these are the strongest field ligands, these are the weak field ligands. You might be surprised to see that our all halides, which are highly electronegative, are weak field ligands compared to these neutral molecules like carbonyl. They are strong field ligands. Let's try to explain why this neutral molecule like carbonyl is so good in complex formation. The answer lies in, when we examine the spectrochemical series, the ligand strength, it is intriguing to see the cyanide and carbonyl are strongest ligands, not the fluoride and chloride. The reason behind is, carbonyl makes a sigma bond with the metal atom. First, it donates the electron to metal. Then, we know it having a p orbitals. And metal sigma carbon sigma bond is formed by the donation of electrons from carbon to metal. And next, metal donates back the electrons to the p orbitals of the carbonyl. This is called a back bonding. Because of this back bonding, in which the d orbitals overlap with the p orbital, makes the bond very strong. Because of the back bonding, metal carbon pi bond or metal carbon back bonding results in the formation of a very strong complex, and this back bonding happens through the transfer of electrons from the d orbitals of metal into the vacant anti-bonding pi orbitals of carbon monoxide. As you know, anti-bonding molecular orbitals are very high energy and having comparable energy to d orbitals of metal, and their orientation is suitable. That makes the overlapping or transfer of electrons from the d orbital to the anti-bonding pi orbital of carbon possible. That is the reason back bonding is responsible for the strength of carbonyl. Metal to ligand back bonding creates a synergic effect which strengthens the bond between carbonyl and metal. So this back bonding is the basic reason for the strength of carbonyl. When we examine the spectrochemical series of ligands, that's what we see. Like, let's see some complexes like nickel tetracarbonyl, strong field ligands. We having a trigonal bipyramidal geometry with iron. Then we having a bridge sort of complexes between cobalt and carbonyl. Manganese forms a bridge structure with the carbonyls Mn2CO10. Then we have a chromium octahedral complex